Okay, I didn't yet read your midterms. I will read them soon, hopefully. And not today, but if you want on Wednesday, we can discuss the midterm questions. On Wednesday, we will have 1 hour of lecture. Remember last week we missed 2 hours of lecture, so this week I will just make up for the, well, last week we missed 1 hour, so we will make it up for this Wednesday. In the first hour, I will do the lecture. In the second hour, we will have a recitation, and if you want, we can discuss the midterm questions. And any other questions besides midterm? This Friday, we will have 1 hour of lecture. In the second hour, I will ask your assistant to come, and second hour will also be a recitation, if you want.
O zaman haftaya çarşamba da mı 1 saat?
Any questions? Anything you want to ask about the midterm questions that you feel so urgent?
Benim kafama şu denklem takıldı. Şimdi biz defterde şeyi yazdık. Delta koyduk oraya ama bunu nasıl o del operatörü alınmış hali onu anlamadım. Ve elektrik alanda da yok del operatörü defterde.
Well, you see, B is the curl of A. It's the curl of mu 0 over 4 pi J R prime TR over R minus R prime. T cubed R prime. And remember, keep in mind that this acts on the coordinate R. So basically, when we are acting with the coordinate R over here, it will act on this 1 over R minus R prime. That's one thing it will act on. So it will just give me this 1 over R minus R prime cube cross product with R minus R prime. And then I have this R dependence. Besides this 1 over R minus R prime, it also appears on TR. So when I want to take the curl of J, J also depends on R. Well, the curl of J will be basically the derivative with respect to the x, y, and z of this coordinate R, but it is only through this TR. So the derivative with respect to x, y, and z will be the derivative of J with respect to the second argument, which is this dot over there, multiply with the derivative of the second argument with respect to x, y, or z. So those are the things that bring this. Well, one of these factors is from here, and this R minus R prime over R minus R prime magnitude comes from the derivative of TR with respect to the coordinates. So there is no gradient or divergence left inside the integrand. Either I made a typo when I was writing it on the board, or you made a typo when you were just copying it on your notebook. Now, today we will start the subject of radiation. Well, basically these equations are Jeffimenko's equations that we had derived. I will need them in a moment, so I didn't want to waste time writing them down during the lecture. So first of all, let's start with radiation. What we mean by radiation. Let's be specific about that. I mean, there are many uses of the word radiation. It's usually perceived by the common people, let's say, as a dangerous word. It's confused with radioactivity also. But radiation is basically anything that radiates. Well, not an illuminating definition, but what we mean by radiate is you kind of send away energy, and in principle that energy can go up to infinity. That is what we mean by radiation. In this sense, for example, these heaters over here, they are called radiators because they are radiating heat. These light bulbs, they are also radiating. They are radiating electromagnetic waves. Similarly, gamma rays that you said, the radioactive materials, they are radiating away energy. The energy, that once they emit the energy in principle go up to infinity. So whenever we are talking about some kind of a radiation, what we mean that the system that we are talking about is emitting some kind of an energy, and that energy in principle can go up to infinity if there are no other obstacles. It doesn't stay close to the object. For example, we cannot radiate kinetic energy. No mass can radiate kinetic energy because kinetic energy is basically attached to the object itself. So it cannot go to infinity independent of my object. Now, in our case, we had already seen the energy in electromagnetic waves, and we had seen that the total energy, total mechanical energy of a given system, let's say in a given volume V, it changes due to the Poynting vector. So if we calculate the total mechanical energy in a volume V, this volume V is the volume that contains all the charges, all the masses, etc. If that total, okay, so this mechanical energy in volume V contains the kinetic energy of my object and the potential energy of my charges. It also contains the energy stored in the electromagnetic field. And if that is changing, that is only because there is a Poynting vector, and we had just, once we derive this relation, we interpreted this Poynting vector as a kind of an energy flow through my surface, through the boundary of my volume V. So if I want to see whether a given object is radiating energy, so the amount of energy, that is radiated by the object should be given by this integral, S dot dA. This is the energy flow over some closed surface. Well, this surface we can just assume it to be a circle with radius r. Let's say, just take it to be a sphere. Centered at my charges. So what I'm imagining here is I have some localized charges over here somewhere, and I take a sphere that is very far away from my charges and try to see if there's any energy leaving my surface. So if any energy is leaving the surface at infinity, which will eventually go to infinity, if there's any energy leaving that can in principle reach that surface, that is what I call the radiated power, radiated energy. So I have a localized source. Well, any physical system is kind of a localized. So by a localized source, I basically mean that something that doesn't extend up to infinity. And it can be, my charge distribution can be the whole Earth if you want. But nevertheless, compared to the scale of the universe, that's a localized source. Now let's see do we have any system in which it can principally radiate? You see, we have in electrostatics, we have the Gauss law. By the way, this dA is the area, not the vector potential. But this tells me that for very large distances, the electric field should go as 1 over r squared. Similarly, in magnetostatics, B dot dA is equal to 0. Well, this is always true. B dot dL will be proportional to I enclosed. But if you imagine a very large sphere, a very large closed loop, its circumference will go as 2 pi r. So the B field should go as 1 over r, so that their product will be constant independent of r. So this basically tells me that any B field that I can create by some charges will go as 1 over r. in the best case, let's say. And this 1 over r dependence, in fact, is linear dependence, 1 over r dependence we only obtain in the case of an infinite straight wire. In a localized source, we know that the B goes as 1 over r squared at very far away distances. But if you take such typical behavior of the electric field and the magnetic field, you will see that the Poynting vector, which is 1 over mu 0 times E cross B, it goes as 1 over r cubed at distances very far away from my source. So this will be, well, this is, again, kind of the best we can expect from the fields similar to the electrostatic or magnetostatic fields. But this tells me that such fields, S dot dA, if you evaluate this integral, well, this will be basically behave like 1 over r. You see, S behaves as 1 over r cubed. If you imagine a very large sphere, the surface area of the sphere will go as r squared. So this radiated power, it just will go to 0. There's no power radiated from such fields. The problem is that the Poynting vector goes to 0 very fast. So the energy is basically localized close to my charges. They cannot go to infinity. This is a non-radiating system. Now let's look at the general case. Well, you see, if we have electrostatics, there is no magnetic field anyway, so S is 0. In magnetostatics, well, most of the time, we can have this 1 over r behavior for an infinite wire. For a finite charge distribution, we will have a 1 over r squared behavior. If the system is charged, in that case, we can have this 1 over r squared electric field. But in any case, even in magnetostatics, we cannot have any radiation. But what about dynamics? Now let's look at the Jeffimenko's equation. These are the electric and magnetic fields created by some arbitrary charge distributions or by arbitrary current densities. You'll look at these terms. These are the terms that we have in the case of magnetostatics and electrostatics. Let's say J and rho, they are very localized. They are localized in a finite volume. If R is very large, then I can just ignore this R prime term. And if you look at this term gives me a magnetic field that goes as R over R cubed, 1 over R squared. So these are the terms that go as 1 over R squared. Similarly, in electric field, if you look at the first term, that is the term that goes as 1 over R squared at infinity. But look at the second terms and the third terms. Look at this term. This is R over R squared. It goes as 1 over R. Look at this one. This also goes as 1 over R when R is very large. And in the case of, but both of those terms, they depend on the time derivative. So it's crucial that we have a dynamic system, not a static one. If you look at the B field, again, this goes as 1 over R squared, but look at this term. This term is R over R squared, so this also goes as 1 over R. So these terms will be basically responsible for the radiation of an arbitrary current and charge densities. So since E and the B fields, they will both have this 1 over R behavior, the Poynting vector, which is the product of the two, it will behave as 1 over R squared. You see, the Poynting vector, if we have time-dependent currents and time-dependent charges, the Poynting vector will behave like 1 over R squared. The area grows as R squared, so in principle we can have radiation. So although the Poynting vector, that is the radiated power, will be very small, nevertheless, it's so small because it is spreading over an infinite surface. So, but nevertheless, in principle, that energy can reach infinity. So that is what we call radiation. Now, we will first start by studying some simple cases, some simple radiating systems. First, the electric dipole radiation.
şey anlaştınız ya, burada niye elektromanyetik dalgaların sahip olduğunu düşünüyorum?
We did. That mechanical energy contains the energy stored in electromagnetic field also. You see the left-hand side, this mechanical energy in a given volume V, this contains the volume, first of all, contains all the charges and masses in my system, and this mechanical energy in the volume V contains their mechanical energy, kinetic and potential, plus the energy of the electromagnetic fields within that volume V. Now, in this electric dipole radiation, you remember what an electric dipole is. We have some, let's say, plus Q charge over here, some minus Q charge over here. For simplicity, I will just assume that they are fixed, but they are time dependent. Their position does not change, but they depend on time. And as a simple example, in the book, it is assumed that Q of t is equal to Q0 times cosine omega of t. Of course, this is possible if you create some current running through it. Let's say I of t is just dq by dt q0 sine omega t times omega. Well, if this is the positive direction of the current, what is it dq by dt or minus dq by dt? Let's see, if q is increasing, then the current is positive. So if dq by dt is positive, I of t should be positive. So it should be plus, so here I have a minus sign. So this is what this is a time-dependent dipole. So if there is any radiation emitted by the system, that is what we call an electric dipole radiation. You see, for example, if you see any antenna of a transmitter that has this straight shape, so you have these straight antennas, they are basically they radiate through electric dipole radiation. How you can create such a system? Well, just take a very large antenna, put an inductor, and then the other end you can just ground it, for example. Here, you can put a capacitor. Here you can have a microphone. And maybe you can put some power source. So basically the microphone will change the amplitude, the power. There is an oscillating source over here. So there you create an oscillating circuit which depends on the level volume of the sound outside. And hence this oscillating current will create some oscillating currents in the inductor, but you see the circuit is not closed, but the charge will go up and down. As the charges are more, the electrons, let's say, if the electrons are going up, there you get the negative charge. On the ground you get the positive charge, or you create a dipole. So this is a dipole radiator, electric dipole radiator. Now later on we will also see that magnetic dipole radiator. Probably you have also seen these antennas that are circular. Have you ever seen them? Yeah. Especially in the old TVs, you either had these straight wires, or sometimes you had these circles. Those circular antennas is what, if you use them as an emitter, those are called magnetic dipole radiators. We will see why. But this is what we call an electric dipole radiator. Okay, now let's start with the potential. Now I will have such a system. We know that the potential at a given point is 1 over 4 pi epsilon 0, integral of rho of r prime, tr divided by r minus r prime, d cubed r prime. And rho of, okay, let me just put my charges also. This is my plus q, this is my, well, let me just draw it in a different diagram. This is minus q, this is, let's say, plus q, and I'm looking at it somewhere over there. Let me choose my coordinate axis. These will be my axis. Let's call that the z-axis. This distance I will call r. This distance I will call r plus. And this distance r minus. And the q, now rho rt is nothing but q of t times Dirac delta r minus, let's say, delta over 2. This vector, I will call it the delta vector. And minus q of t Dirac delta of r plus delta over 2. This is the volume charge density. I have 2 point charges, plus q and minus q. They are dependent on time. One is at delta over 2, the other one is minus delta over 2. This vector pointing from the origin to the plus q charge is delta over 2. And the vector pointing from the plus q charge, the origin to the minus q charge is minus delta over 2. That is that second term over there. So the potential at the point r, at the time t, this point is my point r. This is 1 over 4 pi epsilon 0 q tr plus, let me put a plus sign over there, corresponding to the retarded time for the positive charge, divided by r minus delta over 2. This is the distance from the plus q charge, minus 1 over 4 pi epsilon 0 q of t r minus divided by r plus delta over 2. This is equal to 1 over 4 pi epsilon 0 q0 times cosine omega t minus omega r minus delta over 2 over c divided by r minus delta over 2 minus 1 over 4 pi epsilon 0 q0 cosine omega t minus omega r plus delta over 2 over c. Up to now, everything is exact. There is no approximation whatsoever.
Hocam şurada neden r minus r prime over c denildi? Retardetten için.
What is my r prime?
Şuradaki
You see, we always define tr to be t minus r prime over c. Okay, this is our retarded time. But keep in mind that r is the position at which we are making the observation. R prime is the position of the charge that is contributing to my potential. Now, in this case, my charges are not moving. Now, there are some currents running, so there are obviously moving charges. But this here the total charge is neutral. So there is no charge moving in that sense. It always stays neutral. And the position of my charges are fixed. They are not moving. One is fixed at this point, the other one fixed at minus delta over 2. So R prime is delta over 2 for this charge and minus delta over 2 for this charge. So that's why I have in my expression you see the plus charge is at the position delta over 2. So TR for the plus charge is R prime is delta over 2, R minus delta over 2. For the negative charge, the position is at minus delta over 2, so retarded time is T minus R minus minus delta over 2 over C. Now we will start to make our approximations. First of all, we are looking at a point that is very far away from my dipole, so that the R is much larger than delta. That is the first approximation we will make. We have our localized charge. Remember, for radiation, we should take a sphere at a very distant point. And delta is the size of my system. Well, this will tell me that R plus or minus delta over 2 is equal to, let's say it is R plus or minus delta over 2 squared to the power 1/2. This is equal to R squared plus delta squared over 4 plus or minus R dot delta to the power 1/2. And keep in mind that delta is very small compared to R, or we can write it straight away as R 1 plus delta squared over 4R squared plus or minus R dot delta over R squared to the power 1/2. And just keep in mind that delta is much smaller than R. So this number and this number are very small numbers. And for very small numbers, I can just use the Taylor expansion. So this is around R1 plus or minus R dot delta over twice R squared. Plus or minus R hat dot delta over 2. This is one approximation we will do in the retarded time. 1 over R plus minus delta over 2 will have more or less the same expression with the opposite signs, minus plus R hat dot delta over 2. The difference between this expression and this expression is that here, if I take the plus sign over here, I get the plus sign over here. In this one, if I take the plus sign over here, I get the minus sign over there. So these expressions look very similar, but they are different. But keep in mind, oh, sorry. This is 1 over R. I just take the 1 over R term. No, I made a mistake over there. That will be, if we do it properly, that will be 1 over r times 1 minus or plus r dot delta over twice r squared. I just take it from here. I'm looking at 1 over this expression, that is 1 over r, and then I have the minus 1/2 power. So since I just ignore this one, it is very small. Since there is a minus sign, it changes this sign from plus minus to minus plus, etc. But keep in mind, we had said that we are looking for the terms that are proportional to 1 over r. Look at this term. This is already, the potential is already 1 over r squared. So it will not contribute. I can just replace that 1 over the absolute values as with 1 over r only, up to terms that are 1 over r squared. Now let's go back. This was our potential. So this is approximately 1 over 4 pi epsilon 0 times r. One has 1 over r minus delta over 2. The other one has 1 over r plus delta over 2. I only keep the 1 over r term. And then I have q0 times cosine omega t minus omega over c r plus omega delta dot r hat, well, let's see, over c. This is the first term. The second term is minus cosine omega t minus omega over c r minus omega delta dot r hat over c, plus terms that are proportional to 1 over r squared. Now, I will use the expansion of the cosines. This is one angle minus some other angle. Here, the same angle plus the same other angle. I will just expand them. And if you remember, cosine of a plus or minus b is cosine a cosine b minus plus sine a sine b. Well, I'm talking about the same angles over there. So when I take the differences of those two terms, the cosines will cancel and I will end up having the sines only. With a minus sign, sine of omega t minus omega over c r sine of omega delta dot r hat over c times 2.
Hocam bu eksi nereden geldi?
Well, you see, if you have the sum of two angles, the cosine of the sum of two angles, the sign between the two is minus. Since I'm looking at the differences of the sum and differences of the cosines, these terms cancel. The first term comes with a minus sign, the second term comes with a plus sign, but there's a minus sign over there. Do you agree up to here? I will make one more approximation. By the way, I think I forgot some factors of 2. So here I get factors of 2. Now I will make one more approximation that I will assume that this number is small inside the sign. That is omega delta over C is much, much smaller than 1. Or C over omega is much, much larger than delta. What is C over omega? If C is the speed of a wave and omega is its angular frequency.
Wave vector. Wave vector.
Let's check the units. C has the units of meters per second. Omega has the units of 1 over second. If you take the ratio, whatever you obtain has the units of meters. The wave vector has the units 1 over the meter. Well, this will be the wavelength. So we are assuming that the size of my dipole is much smaller than the wavelength. Now, why do I make that assumption? Well, let's see, phi of r and t is minus q0 over 2 pi epsilon 0 r times sine omega t minus omega over c r. Well, omega over c is our wave vector. Times, if that angle is very small, it just becomes omega times delta dot r over 2c. This is minus q0 over 4 pi epsilon 0 c times r, q0 times delta dot r omega sine omega t minus omega over cr. This is equal to, no, this is r hat. This is equal to d over dt q times delta dot r hat over 4 pi epsilon 0 cr. Keep in mind that q is equal to q0 times sine of omega t. Of course, this derivative is evaluated at t is equal to omega t minus omega over cr. If you take the time derivative of q times delta, it just, the q we had assumed had the cosine dependence, right? If you take the derivative with respect to t, you get minus sine omega t times omega times q0. You have the omega q0 and the sine. So this expression, I can just write it in this form. What is q times delta? Remember, I have this minus charge, plus charge over there, and the vector pointing from the minus charge to the plus charge is what I call the delta. So the positive charge, the charge multiplied by their separation in this dipole is nothing but the dipole moment, electric dipole moment. So this is nothing but the time derivative of the electric dipole moment. Is equal to p dot evaluated at the time, at that time, that is omega of t, that is evaluated at the time t minus r over c. Scalar product with r hat divided by 4 pi epsilon 0 c times r. Of course, plus terms that are proportional to 1 over r squared, which I ignored. Well, you see, this is nothing but the retarded time, assuming the dipole is just a point object located at the origin. So my observation point is at a distance r, so retarded time is just t minus r over c. The important thing will be the phi is proportional to 1 over r. You see, when I'm calculating the electric field, I need to take the gradient of this phi. Now, when I take the gradient of this phi, of course, I will have the gradient of 1 over r, which will become 1 over r squared, but at a very far away zone. Well, that's not important. That will just go to 0. That will not contribute to the radiation. But when I'm taking the gradient of phi, phi depends on r also through this term. So I will get an additional term which has the second derivative of the dipole moment. And that will be my radiation term.
Şu eklediğimiz şey mi? Şu tarafa eklediğimiz.
I'm not adding it. I just ignored all the terms that contain 1 over r squared up to this point.
Şundan gelecek r squared alacağız.
What I'm looking for when I'm looking for a radiation field is the electric field should have this 1 over r dependence. The magnetic field should also have this 1 over r dependence. So I'm looking for an electric field that has the 1 over r dependence. But if the potential itself has this 1 over r squared dependence already, well, the contribution to the electric field will have, in the best case, 1 over r squared dependence on position. So that's not radiation. I want terms that are proportional to 1 over r. When I'm taking the gradient of this thing, the gradient will receive contributions from the gradient of 1 over r, which will be 1 over r squared, which I'm not interested in. But it will also take contributions from the gradient of the p dot, because p dot depends on r. That will be the electric field that has this 1 over r dependence.
Yani elektrik alan 1 bölü R'ye bağlı olacak.
Yes, that is the electric field I'm looking for. And this potential will have, it seems that it will contain, unless it is cancelled by the vector potential. You see, the electric field contains two terms, one from the scalar potential, one from the vector potential. Unless that 1 over r dependence is cancelled by the vector potential, the electric field corresponding to the scalar potential will have this 1 over r dependent part. And at very far away distances, the only important thing will be that 1 over r dependent part. The 1 over r squared parts will be negligible.
Ama sonsuzda gene 0 olacak.
But you see, what I'm looking for is what kind of energy can escape to infinity. You are right, at infinity this 1 over r terms will also be 0, but if you are measuring the total energy that is escaping to infinity, you multiply this, electric field will be 1 over r, the magnetic field will be 1 over r, the pointing vector will be 1 over r squared, and as you said, they will be 0. But if you sum all of them over all of the surface at infinity, the surface is also infinite, so we have this 0 times infinity uncertainty. But the 0 is, it goes to 0 as 1 over r squared. The surface goes to infinity as r squared. The product will be finite. That is what I'm looking for. And this is basically the first term, the potential. Now we have to calculate the vector potential. And if you remember the expression for the vector potential, this is equal to J at r prime tr divided by r minus r prime d cubed r prime. In our case, we can write this as I at tr. This is in the z hat direction. times dl over r minus r prime. So az, A will only have the z component. This will be equal to I of t r dl divided by r minus r prime, or dl is nothing but dz, and z change from minus delta over 2 up to plus delta over 2.
Hocam, what do you mean by integral of time with respect to length?
I'm not integrating over time.
Integral of TR in z direction over
This is the current at the time tr. This is I.
plus minus.
No, this is I. Okay, that we will continue after the break. Now, any questions before the break?
Hocam bir şey soracağım. Hani burada artı Q eksi Q'yu birbirine bağladık ya, akım gidiyor. Geri geliyor mu peki? Yani artı x arasında geri geliyor mu, yoksa sadece eksiden artıya hep gidiyor mu?
Well, let's look at the current. So what is the sign of sine omega t? Is it positive or negative? It changes. Sine can take positive values and negative values, depending on the time. So let's say at t is equal to 0, cosine omega t is q0. So this has the charge q0, this has the charge minus q0 at t equal to 0. Now at t equal to 0, there is no current. Now let's increase t slightly. It's a small positive number. Now it's a slightly positive number. Q of t is slightly smaller than q0. Well, omega t is a small but positive number. Sine of a small and positive angle is positive, so the current is negative. A negative current means that the charges are moving from the plus charge towards the minus side charge. So when this plus q is decreasing, the current is running downward. When this plus q is increasing, the current is running upward. So you see the sign of I of t constantly changes with time. Okay, see you after 10 minutes.